Hi, I'm Dr. Courtney with the Quantitative Reasoning Center. And as we reach the end of Calculus 3, students should consider and learn from their experience as it relates to their study habits and how they approach the course. Many students approach the course without carefully reading every section and trying to follow the examples. Instead, what they do to save a little time at the beginning of the course is jump straight to the homework problems and try and work the homework problems before they've read the section carefully or considered the examples. And they might kind of sneak by a little bit and get on pretty well, maybe through the first chapter or so before things get too difficult. But then when the crunch time comes later in the semester, they're squeezed for time. They try and maintain that habit, the material gets a little harder, and the negative learning consequences begin to show up on the graded events. So let me encourage you, good habits. When you come to a new section in the book, read the section carefully. Follow the examples closely as you're reading. Only after you've read the section and tried to follow the examples rather closely does it make sense to then attempt the homework exercises. And usually what you'll find is that the homework exercises can be corrective. If you get to them and you don't know how to do them, odds are you need to revisit the examples. And as you revisit the examples, try to actually follow them closely. And to help yourself with the discipline of paying attention to the examples and not letting you wash over it, letting the examples wash over you, so you get to the example without really knowing what happened, you can actually try and write the example down. And as you're writing the example down, you might copy down the first couple of steps and then trying to work the rest of the example on your own and only refer back to the way that the examples worked in the book when you actually find yourself unable to complete the steps on your own. And through this kind of process, a few minutes later when you get to the homework exercises, odds are very good you'll find yourself using the same skills in the homework exercises that were illustrated in the examples, and you'll be well prepared. Okay, today we're having a look at 16.2, number 26, where we need to evaluate the given line integral. And the instructions say that one can use a computer algebra system or one of the handheld calculators for actually doing the integral once you get to the point where it's in a form that you can bring technology to bear. So most of our work in the example here is going to be, well, how do you set this up so then the computer algebra system can do all the heavy lifting. So we have an integral over a curve, or a contour, it's parametric equations in this case, of this function ds. So we need to remind ourselves, well, first let's use the idea problem solving format. So I stands for interpret or identify. We want to identify the big idea in the problem, so we want to use line integral. And usually line integral is sort of a little bit sloppy in the language. It doesn't mean necessarily the parametric equation doesn't have to represent a line, but it's a contour or a curve, right? It's some sort of space curve that we're integrating over to find result. And that's not the best, most clearest interpretation, but as we develop it, right, one could graph r of t in 3 dimensions, and the idea is that r of t is wandering around in 3 dimensions as t goes from to 1, and so this is what's happening, and this is the integrand. And what is ds? Well, s is the arc length, if you remember back from earlier work, and one can have an expression for the arc length, etc., etc. And so recalling the results, we can write ds as the magnitude of r prime of t dt. And what does this really mean here? Where does this really come from? Well, if r of t is the parametric equation for the space curve, the position in space as a function of time, then r prime of t is the first time derivative of that. So it's like effectively the velocity. So the magnitude of the velocity is the speed, and s is the distance that you've gone. So this relationship, even though it looks all mathematical and you can kind of get lost in the alphabet soup of it all, what it really means is that the distance you've gone, at least in an instant of time, is equal to the time rate of change of distance, which is the speed, times dt. So we can actually use this. So let's go ahead and develop a bullet point plan, because this relation is important in our bullet point plan. So we want to express integrand in terms of t, and we do that with substitution, and then we compute r prime of t and the magnitude of r prime of t, and we'll talk about that when we get there. And then we will sub in ds in terms of dt, and then we express integral with limits, and then we evaluate with the computer algebra system or a handheld calculator if you prefer. Alright, so now to actually evaluate or to execute the plan we've developed here, well, this is the integrand, and we can use z equals e to the minus t, x equals t, and y equals t squared relatively simply to express the integrand in front of the t in terms of t with the method of substitution. So the integral over c, z we just substitute in e to the minus t. Oops, that's not right. Actually, I was right. Z is e to the minus t. And then e to the minus xy. Well, x is t, and y is t squared. So t times t squared is t cubed. And now we're going to leave the differential blank while we back up here a little bit and we think about ds in terms of dt. So we need to concentrate on the magnitude of r prime of t. Well, r prime is a vector, and its x component is dx dt, its y component is dy dt, and its z component is dz dt. And then to get the magnitude of any vector is the square root of the sum of the squares. So it's dx dt squared plus dy dt squared plus dz dt squared. Well, this is rather straightforward. Dx dt, well, x is just equal to t, so the first time derivative is 1. Dy dt is 2t, and dz dt, well, z is e to the minus t, so the first time derivative is negative e to the negative t, using the chain rule. Alright, now we can complete this idea here. So r prime of t is the square root of 1 squared, which is just 1, plus 2t squared. Well, 2t squared is 4t squared. And then when you square the z component of the velocity, you get plus e to the minus 2t. So ds is equal to this times dt. So we can put in here the square root of 1 plus 4t squared plus e to the minus 2t dt. So now we have nearly completed the setup of our integral by substituting in ds in terms of dt, and now we need to express the integral with the limits. So the lower limit of integration is t equals 0, the upper limit is t equals 1, and that's simply because we're integrating over this region here. So this setup for the integral is complete. So now it's just a matter of evaluating the integral with the computer algebra system.